Hey everybody, this is Josh Valentine with the Clean Coalition. Before we get started, just wanted to let you know who's speaking today. It's John Griffiths from CONTECH and Jeff Harding from ChargeBliss. We also have on hand John Sarter with the Clean Coalition. And John Griffiths is going to kick us off here on his microgrid presentation. Just as a reminder, if you have never used GoToWebinar before, there's a chat box and a question box. If you want to answer a question, ask a question, we'll address them at the end of the presentation. Just enter it only in the question box in your GoToWebinar control panel. So without further ado, I'll hand it off to John Griffiths now.
Great. Well, thank you. And thanks all for taking the time out on I'm sure, a busy Tuesday to join this webinar. So hopefully it will make it a useful way to spend your time. And we're going to talk about the Kaiser Richmond Microgrid. And I think as we go through, if you have any questions, as Josh said, feel free to enter in the chat box. It'd be great to address these as we go on, or we can pick them up later. So let's jump in here. So this is a video we're showing is the actual Kaiser Richmond Microgrid, which we're going to talk a lot about in this presentation. And as we go through, Clean Coalition, and I trust this is in line with your goals, accelerating the transition to renewable energy and a modern grid through technical, policy, and project development expertise. So hopefully what we're going to talk about today is in line with your goals. Agenda, so we'll get to the actual microgrid itself, which is the first high occupancy microgrid in the United States. And we're going to talk about what's driving this technology, the impact of renewables and decarbonization, and how this will help that. I'll also touch a little bit on the regulation. Myself, CONTECH and ChargeBliss, we're also work a lot in healthcare, and we're both on the board of the Hospital Safety Committee in California, which is regulating the hospitals, trying to drive this regulation. And we'll talk about systems and opportunities and how you can apply this to your project. So again, myself, I'm John Griffiths. I'm an electrical engineer. Started out many years ago as an electrician, and now the founding principal of CONTECH-CA. We focus on electrical engineering and distributed generation and microgrids for clients in California, but also around the world. And then I'm also joined on this presentation by the project manager from ChargeBliss, Jeff Harding.
Yeah, thanks, John. Jeff Harding here, the Director of Construction for ChargeBliss. Our CEO, shown here, Dr. David Bliss, and our COO, John Harding, is also on the call. Yeah, and we've been a development team in the green energy space for a little over 5 years, and hopefully this will be a good presentation.
Josh, are you there?
Right. Thank you.
Is there a 9-digit code that people can use to enter this? People are having a hard time connecting. Josh, do you want to share that?
What was the question? Is there a code to dial in audio?
Yeah,
is that what you're referring to?
That it's requesting a 9-digit code.
Yeah. Well, that's probably for audio access. The access code for audio is 700-739-202.
Okay. Okay, so the audio access code is 700-739-202.
Correct.
Sure. It's 700-739-202.
Yes.
Okay. Should I keep going, or do you want me to wait?
No, go keep going. Thanks, John.
All
right. Okay. All right.
Yeah.
So I just thought I'll just do a quick introduction of what a microgrid is. I'm sure many people on here are aware, but I think just for those that aren't. So I use this slide from the Department of Energy. Right now, most buildings are connected to the Microgrid,
Josh,
the
can
utility,
I speak for a moment?
and then
He said the code is no
John,
longer.
you're not. Can you mute John? Josh? So right now we're connected to the macrogrid, most buildings, and whereas a microgrid is connected to the macrogrid or the utility through a point of common coupling. That could be a transfer switch, a smart switch, or even just an open disconnect. So microgrid has the ability to distribute and utilize energy generated within the grid itself, disconnected from the macrogrid. So key components will be some source of energy. That'd be that PV, solar, battery, wind, or even cars, V2B, vehicle to building, or in many cases, diesel generators. So those are in our goal of decarbonization. We're hoping to move away from that. So then, one of the important things that we should focus on today is controller, and I forgot that, but we'll try and pick that up as we go through. And that controller will take inputs from other microgrids, weather forecasting, can storm harden. I think recently, even the Tesla, those with the power walls issued a storm hardening where you would increase the state of the charge in the event, so you have more power available when you lose the utility. And then the other thing will be utility markets. The controller would take in inputs, and that would decide based on economics, what is the best time to charge and discharge these stored assets on the site or the renewables, or whether it's more economic to take power from the utility. So I went very quickly. Feel free in the chat box if you do have any questions. That, in essence, is a microgrid. Key components, a point of common coupling, so you can connect and disconnect from the utility or the macrogrid. You have a controller, source of energy, and inputs to the controller. And that can even be just be a time service. So we jump. I always like to start any presentation or discussion with why. Why even consider a microgrid? So just had this slide, excuse me, some of the things that I think from us at CONTECH-CA and ChargeBliss, we have climate change. We're certainly in the Bay Area in California. We are experiencing prolonged power outages as part of AB 901, where the utilities are turning off utility in a planned way for a prolonged period of time, up to 4 days, or could even be longer. Risk of wildfires. Thankfully, this year has been not as bad as the preceding years, but I think it's something we're going to see more of. The other thing with microgrids, generators. The standard solution to emergency power is a diesel generator, and we use the term stranded asset. Well, when it runs, it's very important, and it provides a lot of value, but it's several $100,000 it needs maintaining, installing, and permitting and designing. It's only really going to give you value in an emergency or a power outage, whereas a microgrid and stored energy solutions can also provide that value ongoing, and also if it is designed to be able to island in an emergency, provide value in a power outage. We also can better utilize the renewables, save money, and this is also in line with global climate goals and corporate climate goals. So one of the things I just want to touch on, I think one of the other drivers for why microgrids is the Duct Curve. And make the bold assumption this educated group are aware of the Duct Curve. Here's our favorite little logo here. I grabbed these charts, and hopefully it views okay on the screen here. But we have it's actually back last year, that we've got the demand curve, and then when the renewables come online around 7 o'clock, we have essentially a glut of renewables because California did such a great job of deploying renewables, primarily solar. And then with stored energy, we are able to, even on site or taking in charging from the utility, we're able to utilize or store that abundance of energy that's generated in the middle of the day, and then deploy that at peak demand late in the, which is now shifted significantly late in the evening. We're just talking about why. There's climate goals. Again, decarbonization, and this is not just a California. I know it's a California group, but this is a global goal. I was meeting with a client in the UK back in July, and even the UK have decarbonization goals, and there's a lot of global interest and rightly so in climate change and decarbonizing projects and driving interest in microgrids, which I think as soon as one of the things I'll touch on is the economics of microgrids, is that with microgrids, a big cost, is cost. So as we're seeing globally more interest and more projects coming online, the supply chain, the global providers, Eaton, Schneider, they're going to increase the market for their products. So hopefully costs will come down and we're able to deploy more. So, and then in preparation for this, I think I already touched on this, impact of climate change. This was actually from my dining table. I came home to a PG&E who are doing a great job of, making sure people are ready for this. A flyer, what to do in a power outage, and then actually showing the zones that I'm in here. And I think probably a number of us are in these climate zones, zones 1 and 2, where we're going to see planned power outages. Another reason why we need to look at stored energy and abilities to provide power on our own site. Excuse me. All right, so what this presentation is really about is the Kaiser Richmond microgrid. So myself and Jeff were deeply involved in this project for a number of years. The Kaiser Richmond microgrid is a California Energy Commission funded project. It is hosted by Kaiser. It's on the Kaiser Richmond Hospital site, and ChargeBliss are the developer of this project. And my role was as engineer record for the electrical design, but I've also been involved in the commissioning and ongoing operation, working closely with ChargeBliss. Excuse me. I have this slide. We've been both feel very fortunate enough to be part of this project, and the most recent one, we hosted a California Society of Healthcare Engineers group presentation, and we had probably 35 people attended. So we're seeing a lot of interest, obviously this group, but also across the industry into how we can bring these solutions to keep, certainly hospitals and essential facilities operating in a power outage, but also how do we can, help reduce cost and optimize how we use on-site energy. So I always ask who's familiar with the Kaiser Richmond microgrid, but as this is a webinar, I'm not. Feel free to add it to the chat box. But I'm going to just walk through this project. So this is an aerial shot from Google Maps of Kaiser Richmond, Kaiser Hospital. It's just north of San Francisco. For those that aren't familiar with it, it's actually the only critical access hospital in the area. Even given Richmond's proximity to the Bay Area, it is a disadvantaged community. And this hospital is a very highly utilized hospital, and it's a big part of the community. So, and I would give recognition in this to the hospital. They actually worked through with us as we implemented the microgrid in our various interconnections. So what have we got? So firstly, we have this microgrid. We have a 250 kilowatt solar array on the roof with the parking structure. I don't think it's similar to many projects. And then that is then connected to a 1 megawatt hour Samsung lithium ion batteries. Those are located in here in the lowest level of the parking structure. And then that is then connected from solar into the batteries. And that is then the batteries connect to the inverter. This is a 3-port Princeton powered BG250 inverter. It has maximum throughput of 250 kilowatts. And then that is in turn controlled by the the controller. And here's Jeff through a switchboard. So if I don't forget, we should talk about the controller because it's very important. This is a Windows 10 controller, mounted in the, in a NEMA 1 box in our electrical room. This is a very, very important part of the microgrid. So we back up a little bit. So in terms of operation, so solar panels, those will charge the batteries, and then the batteries will, depending on the time of day, will then either be, the inverter will decide either to take the solar energy, charge the batteries, or if it's a peak event, then it will deploy the energy into the building. So in terms of overall design, excuse me, sorry if I'm talking too quickly. So solar, then that will then come down into the battery room, inverter, and then from the inverter will to either be pulls out. So it can also charge from the utility. So this line shows the connection to the utility, into the inverter, through the inverter, and it can charge the batteries, or the controller then can decide whether to take the energy from the batteries at DC, convert it to AC, and then inject it into the emergency power, into the normal power system. So I have a couple of diagrams coming up that will show how this operates in an emergency situation, but in essence, in summary, we're taking solar energy, charging the batteries. We can also take utility power off-peak, charge the batteries for use when it's when it's optimal for the system in a hospital. But we also have the ability to grid form or island the project by the use of an automatic transfer switch. So if we do lose the generators and the utility, we are able, through operation of a transfer switch, to power the life safety branch, the critical systems within the hospital, using the stored energy and the solar power for a prolonged period of time. Just in terms of what does that do for economically, excuse me. So this is a graph over time. You can see 2016, 2017. This is the amount of energy we're using. You can see the peaks, mostly from cooling in September. And then as we brought the microgrid online, 2018, you can see on this line, we're seeing some appreciable savings here throughout the year. And in 2019, this is somewhat historic, but we're seeing the similar savings. What this doesn't show is this is savings of actual energy costs, but this is also made up of the demand charges, which microgrid is particularly good at, is offsetting those peaks. So, so this controller, this is a shot of the controller, and let me go back here. Sorry, I'm going a little fast, and feel free to let me know if I need to slow down. So we go back here. So this is the savings over time, and this next is a screenshot of the controller. Maybe a little difficult to see on the screen. This is essentially a dashboard that we have created by UC San Diego, who Professor Raymond de Calfon, who's part of the team and developed our controller. So let me check the time. All right, we're coming up on 9:24.
Hey, John.
So what does this show? Yep.
Hey, you mind if I interject with a question from an attendee?
Sure.
Actually, it's Craig Lewis from Clean Coalition. He's asking.
Hey, Craig.
He's asking, does all the solar generated energy go into the battery first? Also, what is the round trip efficiency loss of energy going in and subsequently out of the battery?
Oh, that's a good question. The honest answer is I do not have a round trip efficiency. Jeff, do you happen to know, or if we don't, we can certainly get back to you.
Yeah, no, actually I don't. And for the first question, actually the controller kind of makes the determination. So it would be shared in the morning as and actually you can see from John's graphic, this top slide, the green line represents the solar production. The red line represents what the inverter is currently doing. So the inverter deploying the energy into the building. So you can see it kind of follows that curve, but then also picks up where it's higher than the green line there. That's actually pulling from the storage. So it does both. Some of the solar goes into the building immediately, and some goes into the battery. It's kind of shared. It's based on economics. As far as the round trip efficiency, one comment I would say. The beauty of the 3-port Biggie 250 is that the solar, so there's 2 DC ports and 1 AC port. So solar into battery is a pretty high efficiency because it's DC to DC. But then, yeah, I'd have to get back with you on the exact efficiency rate of the DC to AC. I want to say around 95%, but don't quote me on that. Hope that helps.
So there's a follow-up from Craig asking, given the battery is designed to take energy from the grid, in addition to and from the battery, does the battery qualify for 100% tax benefits?
Yes, I think the threshold is 25% from the grid to qualify for the self-generation incentive. Yeah.
And
we of course we of course worked in the metrics of that into the algorithm of the controller to ensure that we don't go over that threshold. And typically we will charge more overnight in the winter than in the summer. But yeah, that's kind of all worked into the metrics.
Great, thanks. And just another quick question from Malini from the Clean. She's a colleague from the Clean Coalition.
Okay.
She asked, did you deploy the solar PV as part of this project, or was it already in place?
No, it was built as part of this project.
Awesome. All right. Great. Thank you.
Great questions. Yeah. Thanks, Jeff. So feel free to interrupt me as I go through this. I want to make it meaningful for everyone on the audience. As Jeff rightly said, so I'll quickly run through these slides, and we do a time check here on 9:30. Excuse me. So yeah, so in terms of the inverter, so this is, as you're right, you'll see the solar, the green line. That starts to produce. This is around 7 o'clock. You can see this standard solar curve, and then one thing Craig you probably picked up here is this is actually negative. So this is the inverter charging using the utility using off-peak energy. But that is, as Jeff already said, that input is optimized to not exceed the requirements for the SCHIP grant. I think it's 25%. So as we come through the day, the inverter, when the highest loads and the energy is the most expensive, the inverter red line that's gonna when it's deployed most energy. So what does that mean in terms of this is a point of common coupling. This is the actual, I guess, the net energy in the building. So, and again, I hope, Craig, can you see this, the mouse, or I don't know if people can zoom in. I probably should have made these 3 slides. So we've got the blue line is the uncontrolled. So this is the hospital's profile when you're if we didn't have a microgrid. Whereas the red line that's the resultant, the net energy usage. So you can see here, if we didn't have a microgrid, the hospital would be using less energy because it's lower, but because it's charging here overnight, it's going to be using more energy. Whereas then we get to here, when the peak energy use of the facility, that's when we're deploying most energy from the microgrid, from the battery, to offset the peak energy pricing. And again, this is constantly refining algorithm. So it's uncontrolled is the red line, that's the net energy, and then uncontrolled is what it would look like without it. And then just as they do that, part of delivering a microgrid, we had to put in some very, I would call them high fidelity metering. And that gave us a couple of advantages. We actually identified some issues on one of the chillers because we could see this great big spike occurring during the day. And then we worked with the facility and they identified there was a problem with one of the chillers. So kind of a side benefit of installing a microgrid is you will actually have a really fine view of your electrical system, and that can be used, and hopefully in the future in the controllers, to do some diagnostics on systems. So the final slide, which is probably very hard to see on the screen, is the battery state of charge. So you can see the blue line here, the reference, but that very closely matches the measured. So, but it deviates just a little bit here as we get late in the day. So what does that mean? So really, this is good for us because our algorithm is pretty closely matching our reference, what we planned. And I think if any of you, maybe a takeaway from this is a pretty important thing to watch, because we have seen when we've had some unusual weather or power usages on the site, you can see how that, that will deviate through the day. So last other pointers on this slide before I move on. So we see maximum state of charge is 80% and the minimum. So the maximum is, obviously we don't want to, overburden the system. This is optimized to get the longest life and the best performance in the batteries. But the other is the minimum state of charge. So we keep this at 41%. And I mentioned earlier, so this minimum state of charge is how far do you discharge the batteries. And two drivers I have for this are obviously economic in a normal operation, but we don't want to drive it too far down, because what we have had is if there was a chiller or an elevator or some testing that occurred during the day that we weren't prepared for, then the battery would not be able to deploy, and then we would exceed the maximum energy for that month, and then we could be levied a high demand charge for that month. So this optimizing this number is very important to work with your controller developer and your team. And the other thing, we're not actually doing that, but certainly on other systems as we deploy microgrids for to provide emergency power or backup power, is when you have this called storm hardening. In California, our major event is seismic, so you can't predict that. However, certainly with the wildfires, or if you're in a facility or building that had a notification from PG&E that you were potentially going to be, they're going to turn off the utility for a period of time, you could then work with your developer or your controller to not drop below 80%. So you would then be paying more for energy during that time and be hit with demand charges, but you know that you have the maximum stored energy for that power outage. So, and there's any other questions? I'll move to the next slide.
Yeah, John. Craig is asking, how will PG&E's coming TOU charge changes affect the battery charge discharge scheduling?
Another great question, Craig. Thank you. So this is optimized for that. I know, that's having a radical change. Certainly on the Southern Cal Edison, you even have critical pricing. So that is being addressed. As part of the controller. And I think for the rest of the audience, I guess I should probably have a slide. I did have a slide for that, and I took it out. And traditionally the peak time of use charge was midday. Now it's been moved, recognizing the abundance of renewables to later in the day. So we have optimized for that, but certainly any controllers, if anybody does have a controller or any demand response, they should make sure that is updated to reflect the change in time of use charges. Did I answer the question? The straight answer, Craig, is yes, it has been optimized. So we leave time for questions. So this is for those electrical engineers or those interested. This is actually the single line for the hospital. So because this is a critical facility, is an essential, it must be operational for 72 hours in a power outage. I'll quickly run through this, but we have normal power source. In the normal operation, the power comes from the utility to the essential systems through the 3 branches of emergency power. And then normally the PV and battery will charge or discharge through the inverter, and then that will then be absorbed into the system, no different from any other solar PV system. So then, in an emergency, if we lose the utility in a hospital, they have 2 750 kilowatt diesel generators. Those will then power the essential, the emergency power branches. And then part of Rule 21, the microgrid and solar will then shut down. However, the unique aspect of this project is that we are able to, through the operation of a non-automatic transfer switch, grid form the inverter and microgrid system, and then transfer the power. We will then use the stored energy and the solar energy power to support the life safety branch, which is in the hospital is the highest level of priority. That's fire alarm, egress lighting, and some critical systems. And we're able to do that for, well, we tested it for 4 hours, and we had the ability to do it much longer. And then in a prolonged outage, what we have to do is, because this is a hospital, a lot of this is driven by the codes, because at the moment, because this is part of the emergency power system, any component needs to be seismically certified. It needs to be able to essentially not fall apart in a major seismic event. These are very resilient components that we've used, but they're not actually to be able to provide that in a normal power outage. But we do have the ability to support the life safety system for a very long period of time in that power outage. Should they run out of diesel, lose a generator, or use a utility. So with that, I'll just, again, feel free to ask questions. I've probably gone a little quick, just be mindful of the time. This is another project that myself, at CONTECH and ChargeBliss have been involved. The Kaiser Richmond project is actually an essential hospital. It's high occupancy. It's regulated by the state. Whereas this next project we're going to talk about is the San Benito Clinic in Hollister, California. The team was approached by the CEO, who was she's Puerto Rican. She went out and helped in the event of the hurricane there. She came back and said, "This has not happened on my watch." She went to the board. They've agreed to fund a microgrid, so this facility can run I would say indefinitely using renewables on site, and also during normal time. So with that, I'm going to hand over to Jeff, who is deeply involved in this project. Jeff, do you want to talk us through the San Benito project? And before I do that, this has only just gone live, so we don't have a whole lot of information, but it's a pretty exciting project.
Yeah, thanks, John. So the San Benito Health facility, the project consists of, as you can see here, this is actually a look of the dashboard from the Elm field site controller. Elm is a company out of Texas that we partnered with on this project to supply the packaged controller battery system. So the project consists of, as you can see here, 87 kilowatt of solar on the roof of the hospital, a little bit over a megawatt hour of stored energy. Then that's coupled with a EPC 250 kilowatt inverter. So we can supply at any one time 250 kilowatts of energy. And then that is also tied in with an existing 150 kilowatt generator that was already on site and required by OSHPD regulations. The hospital basically runs at around an 80 kilowatt peak. So you can see that there's enough energy there in the generator to not only supply the building with power, but would be able to charge the batteries. Actually, I should back up. So the ideal that the hospital would like, obviously, to run as much off of green energy as they could physically put into the building, but then also have the resiliency to essentially remain off grid indefinitely. And they can do that, as you can see, as you could imagine, at 70 kilowatts with an 84 kilowatt system and a 250 kilowatt inverter, that they can cover the needs of the building almost 100%. You can see from this graph down here that breaks down the green being the renewable energy, the yellow being grid energy, and then there's a little sliver of red that is the generators. And it might be a little bit hard to see in this, but I think during generator testing is when we see a little sliver over on the left.
Yeah.
So basically, yeah. Well, I mean, even during a prolonged duration of no sunlight.
Oops, sorry, Jeff.
Oh, that's okay. Even during a prolonged time of no sunlight, the batteries are being depleted. Then the controller would actually kick in the 150 kilowatt generator, be able to supply the full building load, but then also spill over and charge up the battery. So thus prolonging the life of the, I think they require 4 hours of diesel for this particular facility, but you can see by charging the battery back up, obviously the controller then would switch right back to running off battery power and dial down the generator, or even shut the generator off. One other thing I guess I would note, this has been on for about 8 weeks, maybe a week or so that was commissioning, but as you can see on the left, the total energy consumed from the facility is 34.98 megawatt hours. And from that, of that 35, 21.85 megawatt hours has come from renewable energy. I did the math, and that's about 62% of their energy needs has come from this system. So yeah, I think it's kind of a neat project in that this facility could not only stay open during normal business hours, but could also become kind of a safe haven for the community during prolonged outages.
Right. Well, thank you, Jeff. That's yeah. I think whilst the Kaiser Richmond project was a unique hospital, I think this is a tremendous project to show that how you can use renewables to how you can optimize use of renewables to operate this facility, but also this is a very resilient system in what is a really key part of the community. So just one thing is for the electrical engineers out there, which sort of I honestly hadn't realized the benefit of this configuration. The reason we have the diesel generator is it was already on site and it's actually recently been replaced. However, one of the problems with a generator is testing, and every month when you test it, you need to have a minimum of 30% load. And oftentimes that's quite difficult to achieve. And if you don't get that 30%, you get something called wet stacking, and generators can not start if you don't properly maintain it and you need to add load banks. However, in the way we've got this configured, when they actually run the generator, they can run it at an optimal load for the generator which is very efficient use of the diesel that's possible. To use that energy, typically it's just, either if you have a load bank, it's just wasted as heat. But you can use that, the full capacity of the generator, one, to charge the battery so that energy is not wasted, but also it's basically the microgrid acts as a load bank. So there are other added benefits for this configuration. Great. So Jeff, should I jump into the how to apply that on the project? Did you have anything else to add for San Benito?
No, unless there's maybe other questions or comments. Thank you.
Yeah, and I wish we had more information, because this is a really great project.
We do have a bunch of questions, but I'll let you we're already at quarter.
Okay.
So I'll let you guys finish the presentation.
Right. Great. Let me speed up here. So I just put it through a couple of slides here, how to apply it to your project. So when we talked about this before, I think about two scenarios. There's a new construction, new build, greenfield site, and then there's an existing. So I think really it's, looking, there's most things. If you do want to incorporate microgrid or stored energies, look for that early. Incorporate in early planning infrastructure. Look for opportunities to make the systems forward compatible. You may not have the financing or the space, but designing the systems ways to connect that, because doing it afterwards can be very expensive, and particularly in essential facilities where you cannot shut the building down and you have to have backup generators and interconnections when you do that. These are the opportunities, and again, minimize legacy systems. I use that term forward compatible, but looking for systems and connections and interfaces that will set you up for the future, because things are, innovations happening at a rapid rate, certainly in microgrid and stored energy solutions. Challenges: funding. Where do you get the money? Regulation. In hospitals, we're ChargeBliss and CONTECH. We're actually at the state level to make sure that codes and regulations are catching up to allow us to embrace these technologies. And design skills. I think it's delighted that people are participate in this, because it's important, right? Energy. There's a lot of specialty skills you need and things that we haven't done before. So really, we need to be advocates for this with different groups and educate. On an existing facility, much the same. Opportunities and challenges is on a new build. But one thing I would take away from when we've done these workshops is take the incremental approach. If you're an example I use is, let's say we want to put a containerized system. One of the bigger costs are obviously the container, the interconnection, but it's getting the power from the container into the electrical room. So if you're remodeling a parking lot and you know that that's going to be a perfect location for your battery or storage, put the conduits in between the electrical room and put some conduits in, or think about pathways when you're doing these smaller developments. Or and the other thing is, what we have had is people have entered into long-term PPAs that you may have a lot of solar on your project, but you can't utilize that because that's owned by another PPA group. So let me speed up here, because I just realized what time it is. And in cost, Jeff, I don't know if you have anything quickly to add here. All I would say is, there's a lot of costs involved in this and in other projects, but I think we're probably, the batteries we bought at Kaiser Richmond, we could buy those now on the market at probably 60% less than what we paid for them 4 years ago. Jeff, do you have anything else to add on the cost?
No, I think that's the important point, is that the cost of batteries dropping rapidly over time. Yeah, that's been one great benefit. We've seen projects go from a 4 or 5 year simple ROI to down to 1 and 2 now. So the equipment cost has dropped significantly to help that.
Great, thank you. And then, so in summary, we talked about, why even consider these? What are the drivers of change? What is a microgrid? We talked about 2 examples. One was a critical facility to Kaiser Richmond, and also San Benito, which is very important to the community, but not code required to be that way, and then how to apply it. And then we kind of skirted on the cost, but we can talk about that in the Q&A. So with that, we'll jump to questions.
All right, thanks, John and Jeff. Why don't we go through some of these? All right, from Ryan Stoltenberg comes a question. Ryan asks, what percentage of the hospital's overall load can be covered by the microgrid, not including the pre-existing backup generator?
So, Jeff, should I take that?
Kaiser, it's kind of an interesting project in that we were limited by 2 factors. The first, obviously, the funding amount from the California Energy Commission had its limits. And then also the kind of, I don't want to say antiquated infrastructure, but the older the main bus capacity of the hospital. We were essentially limited by the size of amount of power that we could put in. John could speak better to this.
Yeah.
Based on the bus rating. So essentially we were limited somewhat. So in this case, you know, the hospital runs around a 750 kW peak, you know, almost all day long. And our system can interject 250 kilowatts at any one time. Now, not for a full 24-hour period, but it's optimized based on the peak pricing of the utility. So essentially, we're probably around a 25 to 30% we can cover for the hospital.
Great, thank you.
Great.
I have two quick questions we can rattle off. Malini from Clean Coalition, she's asking if you can repeat the inverter manufacturer name.
It was Princeton Power.
Great, thanks. And Craig is asking if you could confirm that the solar and battery are DC coupled.
Yes, through the 3-port inverter.
Excellent. And also from Craig, we have another question. Can the solar plus battery keep the diesel generator off unless the minimum SOC is reached on the battery? If yes, has there been analysis for how much the diesel fuel can be extended?
Gosh, that's a good question. So, so on the Kaiser Richmond project, make sure I answer that question correctly. We, because this, you know, basically the codes don't allow the microgrid to provide emergency power backup. The only way we can do that is in the event of a failure of the diesel generator that runs out of fuel. So we don't. I guess on the San Benito project, Jeff, do you know if that analysis has been done
yet? What? I don't know that anybody's done that analysis, but I think that would be pertinent information to try and at least do some kind of back of the napkin math. So future. Thank you for that great tidbit of information. We should probably figure out how to share it on the future.
Could you just say the question? Sorry, Jeff. Can you say that question again? I want to make sure I answer it.
For the
generator?
Oh yeah. You know what? I've been I actually erased it, but
oh, don't worry.
Well, you know what? We generate a list of questions in a spreadsheet, so I can send them all to you.
Okay.
Excuse me. I was hastily. I've been erasing them as I go through, but just to clear them out. I won't do that again. So, how about EV charging infrastructure? Is it added to any of these projects? If so, how do those affect the economics, especially with respect to demand charges?
Great question as well.
There was EV charging added at the San Benito project, but you know, unfortunately, I guess since we've only been in operation for 8 weeks or so, we don't have information on that. But yeah, that is a great question. I couldn't even say how well or how, you know, if they're actually utilizing the chargers at the facility. I imagine they are, so I'm sure somebody would. But yeah, sorry, I don't have an answer for that.
Yeah. Well, I could maybe follow on, because we do, as part of our project at San Benito, we're certainly installing EV chargers, and the same at Richmond. You know, Kaiser are providing some pretty substantial EV charging infrastructure, and I think overall, I think that is a great challenge and also an opportunity. You know, as a EV owner, you know, when you connect an EV, that's a significant load that's going to be added that 20 or 30 EVs, that could potentially be the biggest load on a building. But I think also looking forward, and we haven't done that, I mean, tracking that is, let me get it right, V2B, you know, how, you know, we have a huge amount of stored energy in these cars, and certainly in an emergency situation. how can we optimize the use of that? And maybe that, if that's a subject for another presentation with Clean Coalition, I think it's a great challenge, but also a great opportunity.
Excellent, thanks. All right, so Ted Tiffany asks, have you experimented yet with optimizing for carbon intensity on the grid versus optimizing for cost yet?
I think San Benito, it's early, so we've only just got it commissioned. And certainly at Kaiser Richmond, we have not, but that is a great question. Jeff, have you
No, I don't know.
that?
I mean, I can't speak to we are still under the controller development. So we have a team of engineers that are adding, ADR 2.0, so automatic demand response, the signals that come from the utility. We have not looked at that, or they haven't, as far as I know of. But that is a good point to bring up to them, because at some point that may weigh heavier, have a larger value, I suppose, than just your basic economics, utility economics, right? I suppose maybe if there's advantage to having some kind of carbon credit or something, then that could actually, benefit more than just the economics of the utility fees.
Yeah. So maybe if I could build on that, I know Kaiser, they are, I hope I get this right, they've made a very big push, and I believe they are, all their energy they procure is, carbon is from renewable sources. Interesting, I'm working with a client in the UK, and they actually installed a lot of their demand response was using generators as a prime source. So now we're working with them on identifying how we can essentially decarbonize their systems. So yeah, that's a really great question. Particularly as we transfer, obviously costs are very important for facilities, but as we transition into how can we decarbonize systems, and another point is I'm working on another systems is that. Keep coming back to decarbonization. So the electrical loads are going to increase in buildings, and that's a really great question, Ted. Is that we're going to move from gas, water heating, and in certainly hospitals, how are we going to move from these huge loads that are provided by gas, and non-renewable to a renewable decarbonized source. So these are some great questions, but also some really fundamental challenges we're going to be facing and we have to deal with to get to a fully decarbonized grid or systems.
Great, thanks. Melanie from the Clean Coalition asks, why can't the microgrid be used to supply the emergency loads and use the existing genset emergency power system as the backup to the backup?
Great question. In a hospital situation, I think I touched on it before. One, right now it's not, the codes do not allow that from a pure code system perspective. And also on the component side, anything that provides connection to the emergency power system needs to be in a seismically compliant building, and it also needs to be all the components need to be seismically certified. They need to be on a shaker table. This building, whilst it's very robust, this is not, a hospital needs to be operational after a seismic event, whereas a normal building, a B occupancy, simply needs to be safe to exit. But certainly in the future, and then, like I say, myself and David, we're working at state level to hopefully get the codes to catch up with these needs.
All right, great, thank you. Why don't we go with John Sarda's question? Are the EV chargers bidirectional capable for added energy storage?
Kaiser Richmond, not Jeff. Do you know that?
Not at Kaiser, and currently not at San Benito either. So unfortunately not at this time.
And John also asks if Kaiser is considering developing microgrids at other facilities in the Bay Area and elsewhere.
Yes, a lot. Yeah, Kaiser is very committed on many of their facilities.
Cool. And Alice LaPierre asks, I may have missed this, but what kind of batteries were used? What size? What technology? So we've gone over that, but you can just reiterate.
Yeah, sure. It's Kaiser. It's a 1 megawatt-hour lithium-ion Samsung batteries. Jeff, what was the?
Actually, same Samsung. It's a Samsung SDI lithium-ion. That's also at San Benito, and I believe it's like 584 megawatt hours.
Yeah. Can I maybe just add one thing to there? Maybe a takeaway is, if you're, to avoid demand charges, uptime is really important. And I think we've had a good experience of working with Samsung from a technical support. And if you're looking at when you buy your battery technology, which I'm going to use the term batteries and solar are somewhat a commodity, it's very important to making sure you will get on-site support in any commissioning or setup. I think that's a really one of my takeaways from this project.
Great, thank you. Malini asks again, can you give a bit more detail on the not auto transfer switch used in the Kaiser Richmond microgrid, like the brand, model, and capabilities, perhaps?
We can. Bear with me. So we use the ASCO. It is a seismically certified switch. I'm just trying to find the slide here. Unfortunately, I don't have a picture. So it's ASCO. I can't remember the model. Jeff, do you remember the model?
No, not off the top of my head, but I'll call up the submittal sheet.
Great. Alice Sung is asking if there's a case study being written for either project.
So Kaiser Richmond, the CEC have commissioned Navigant, and that is actually on their website. I can send out the link to that. And then San Benito, I'm sure there is, but we've just gone live.
Also, yeah, there was, just provided by ChargeBliss through the CEC grant funding. They call it the final report, but included in the final report is a case study, and you should be able to find that online if you just Googled CEC PON 14301, and I can supply that information if somebody wants to drop me an email.
Wonderful. And Craig is asking, what percentage of the normal loads are the critical loads?
Oh gosh, the critical loads is around. I think Richmond is around 40%. Kaiser Richmond, and then Jeff, do you have the San Benito?
No, I don't know at San Benito, but yeah, I would agree with you at Kaiser. And the reason we know is that the first Tuesday of every month, they do their generator testing, and the hospital, as I said, ran around 750 to 800 kW and would drop to 300 kW or 400 kW, which would be just covering the critical loads. So yeah, maybe it's closer to 50%, John, but yeah, 40 or 50%.
Right.
Great. And Craig had made a comment, more than a comment than a question earlier that I didn't get to yet, but this might be a good place to conclude. If you have any comments to this comment, he states that note that the tax benefits are reduced, if not 100%, under 75% from solar means that no tax benefits extend to the battery. So if you have a comment on that, by all means.
Jeff, do you want to? Do you have any comments on that?
Yeah, sorry, I was looking for the ASCO number. No, is that for as the ITC? Because I'm under the impression that the whole battery and solar costs, we were able to take the 30% ITC credit. But maybe I'm sorry, I may have missed the full question.
If you want to send the comment through and like that, we can give more specific answers because
Yeah.
we've both been very engaged in this over the years, so we got a lot of information we're happy to share. So we can do that in a follow-up note.
Perfect. Well, this is a great place to start. I thank you both for putting this presentation together and presenting and going through these questions. I just wanted to remind everyone who's still on the call, there's quite a few still on the call, that we do have a recording of this webinar, and John Starter from the Clean Coalition will be sending a link to that to view, as well as the presentation itself. So thanks again, everybody, and you have a great rest of the week.
Thank you for the opportunity.
Yeah.
Take care, guys.
Yeah, and thank you everyone, and thanks for some great questions. And again, feel free to my contact information there, and if you have any specific questions, we'd love to talk to you about your projects and share with what we know. Thank you.
All right, thank you. Great job. Talk to you soon.
Thank you. Bye-bye.
Bye.